students used to call me Mike, by the way, but never mind. And before I say anything else, I'd like to thank Sandy. I'd like to thank everybody involved in organising these 2 days. For us, it's a real pleasure. So I'm going to talk about this new operating system we're doing for multi-core systems. My colleague Alex, who's sitting up there, he was at a meeting a couple of months ago, and somebody said, why on earth would you do another real-time operating system? Aren't there enough of them there already, including hypervisors and so on and so forth? So hopefully at the end of the next 10 minutes or so, we'll have a kind of answer for that question. It's not just the operating systems that are different. There's a lot of them. The embedded systems themselves, it's worth realizing, are different. So the first thing we had to really think about was what kind of embedded systems were we targeting for this operating system? To see if I can work this. And what sort of characteristics do they have? You have to decide what you're going to put in. You have to decide what you're going to leave out. The first thing we decided to leave out was handling virtual addressing, page tables, and all that. Most real-time, most embedded systems, the code is fixed once the system is done, doesn't change thereafter. You can get away with using physical addresses. The system has to be robust. To us, that was a critical consideration. And as regards the design of the system, that has a number of implications. There are real-time operating systems out there, for example, where it's possible to get unbounded priority inversion. Happened a long time ago on Mars, I remember. There are a whole bunch of other problems like that can occur. If you choose a different design, you can exclude them by the design. When you have something happening in an embedded system, and it's being controlled by an operating system, which you did not write, it's really an advantage if you can keep an eye on what's going on and be able to police your assumptions, being able to check to see, are things behaving the way you expected? So one of our objectives was to try to make that as easy as possible. So you want the application to be able to check for problems, and the operating system itself should automatically check for them. And when it does find a problem, you want to have it set up so that it can automatically call an application-defined problem handling function or whatever. You also need to provide a number of things that can be done, such as, for example, taking a CPU out of use, disabling tasks, killing tasks that are already running, or whatever. But despite all that, as is well known, things can still go wrong. And in most descriptions of this kind of thing, you see people talking about FDIR, fault detection, isolation, and recovery. We think that it's really also important to try doing fault anticipation. You want to catch the puncture in the car tire before the wheel goes flat. So we want to provide support for keeping an eye on that kind of thing. If you have multiple CPUs in a system, such as the GR740, what are you going to be doing with them? One of the things you can do with them is you can use them to speed up execution of things, running stuff in parallel, and so on and so forth. A different thing you can do is, if you get suspicious that some CPU isn't behaving as it should, you can try running multiple CPUs on the same code and checking the results. You can try using redundancy in that way to help make sure that your system is really robust. So in OCEOS or OCEOS MP, we automatically check these things whenever the system is in use, log things automatically, and so on. And you can do these other things, disable CPU cores, restore them, etc. So based on these kind of ideas of the requirements, we based the design on something called the stack resource policy. There's a nice paper about it written by Baker back in 1991. It has a number of real advantages. One of them is that rather than needing a separate stack for each task, you only need one stack per CPU. Another advantage is that unbounded priority inversion cannot occur. Chained blocking cannot occur. Deadlocks cannot occur if you only have one CPU. Unfortunately, well, fortunately, we've more than one CPU. We cannot exclude deadlocks, but we do warn about them. So we designed the system to be deterministic, behavior completely, really very predictable, to support schedulability analysis so that you can sit down and you can be pretty confident because the timing it takes for the different operations within the operating system is all bounded, well-defined, and so on. You can do your schedulability analysis. You can be pretty confident of the amount of time each thing takes, and so on and so forth. And we record all kinds of details about, what the time is between requests to start a task, what the time is between a request to start a task, and the time when the task actually completes. So we keep track of the minimum of the first of those, the maximum of the second, and we're having a debate whether or not we should also collect some statistics. It would be very easy to keep track of the variance of those things, and so on. Another thought, because we have over many years been doing embedded software, another thought was that it can be, there's a lot of emphasis on not missing a deadline. It can also be a nuisance to be earlier than it. And it can be quite tricky in a way to set things up nicely so that you can guarantee that a certain response to an event happens a certain amount of time later. So we'd set things up so we have these timed actions, and the two basic timed actions are to do a certain output at a certain time or to put in a task start request at a certain time. So what else can I say about it, really? The system is designed so you can exclude some cores from use. So, for example, as was mentioned there earlier, you have 4 cores in the GR740. You might want to use 2 of them for this operating system, 2 for something else. It's no problem. If you have more cores still, you might consider setting Linux going on some of them, having everything going on a different one. You can reserve cores for use only by higher priority tasks. So you can be confident if something really urgent comes along, there'll be a CPU there to pick it up. That's a fairly inefficient way of doing it, I'd have said, but never mind, it's certainly possible. And we've started implementing this. It's not completed yet, but the couple of key things we wanted to make sure were being done properly by the scheduler. One of them was distributing the work that was there evenly over the available cores, so that if a lot of work came in, every core would contribute to getting it done. And also, we could restrict certain tasks to only running on certain cores. I'm not sure we should continue with that, but that's neither here nor there. And of course, we can take cores out of use, put them back in use. So the system is fixed priority. Each task has a fixed priority. One of the reasons for that, originally we intended to use earliest deadline first priorities because they give you advantages with respect to CPU utilization, particularly for periodic tasks in particular. But actually it was ESA who requested us at some point use fixed priorities, otherwise life gets too complicated, or words to that effect. You have preemption thresholds. And for each task, you have multiple execution instances. So for example, you can have the same task running on multiple cores. Those execution instances might just be being used for checking that everything is working okay. They might be used to spread the work across the different cores or whatever. And we have that timed action thing I mentioned earlier. We have mutexes, read-write mutexes, counting semaphores, data queues, kind of the usual thing, I would say. The read-write mutexes in a multi-core setup are quite interesting. One of the things you want to ensure is that the write acquisitions take precedence over the read acquisitions, so that no write acquisition can succeed if anything is reading. But once there's a write acquisition, you want to make sure that no other read acquisition begins. So the write acquisitions take precedence over the read ones and so on. Also, you want to make sure that the write acquisitions, when they succeed, are done on a first-come, first-served basis. So if various tasks are trying to write to something and they ask to do the writing at successive times, you want the actual writing to be done in that same order. And here's some numbers. So we've designed the thing to cater for 255 cores, up to 255 tasks, each task with up to 15 execution instances, and so on. And the core kernel, the amount of space for it is just less than 20 kilobytes. And of course, the fact that there's only one stack per CPU rather than one stack per task can be a significant saving in the overall memory requirements. So things look a bit like this. So part of trying to make sure that the application can easily figure out what's going on, all the data that the operating system uses is statically allocated in 4 main areas. The one on the left is for the system log and for an optional context switch log, and also for a system state variable and a couple of other things like that. The fixed data area is set up at the very beginning, and it contains all the data that doesn't change subsequently as the system runs. And that includes things like, for each task, what the task priority is, what its preemption threshold is, how many different execution instances you can have, and I dare say a couple of other things that slip my mind. The dynamic area holds the information about each task and so on that changes as things happen, like the times. These areas are all protected with sentinels. They can be set up in the application code as arrays. Their sizes are predictable in advance. And the actual stack stuff then, you have a separate stack for each CPU and so on. So the tasks are there with their different execution instances. It's a fixed priority, it's a preemptive scheduler, I need hardly say. And you've got these features there for use. Using it is really quite simple. First of all, it's a library. The stuff that's pulled in is only the stuff that your application needs. Secondly, it's a servant, it's not a master. On a machine such as this, obviously things start up, and the next thing you know, there's an operating system running, and it controls everything else that goes on. In this system, things start up, and at some point you get into main, and when you've got into main, you do a couple of things. You can configure the system using a few calls we have for initializing, basically specifying how many tasks, how many this, how many that, and so on. Then you have to create the tasks, giving what the priority is of each one. And then you wrap things up with this last function. And now the fixed area is complete. The sentinels are there on it, and there's an exclusive OR checksum at the end of it to make it easy to see if somebody has done something nasty to it. Finally, you actually then pass that fixed area to a routine that starts the scheduling, and at the same time you pass the routine that you want to kick things off with. So we've got debug support. Now this comes from just the single core version. just using the optional context switch log, showing things happening this way and that way and the other way, I guess. The current status and how this started, and to go back to the question, the original question that Alex was asked, why on earth do another real-time operating system? It was just, ESA were developing the GR716 with Geisler, and there was a request for an operating system for it. And we've done a lot of embedded software, and we've just been doing another thing. Hey, it was an interesting project. So we got stuck into doing that, completed the one for the GR716. It's got additional support for things like the memory protection features and so on the GR716, and it's ready for ESA flight qualification level B. With the multi-core, really, we've gone quite a long way in it. But the key thing to us was making sure that how we organized the scheduling was working well. One of the tests we did on that was get 1,000 tasks started, putting a real backlog on the system, and making sure they were all distributed evenly among the CPUs. We had done a bare metal version of the fast Fourier transform for 4 cores, so it was an easy matter to port that to the version of OCEOS MP running on the GR740. And the speed up we got when we just did it on bare metal, I remember, was a factor of about 3.68. You know, faster to get 4,000 entry FFT done, with complex numbers in each entry. So the speed up factor there was much the same using OCEOS MP. And the last 2 lines there, there's something to do with marketing, which is not my area, really. So that's about it. So thanks very much to, it's been a pleasure for the GR716, I must say, it's been a pleasure working with the people in ESA, and thank them for the support on that, and the support on this current thing. And thank you for listening. I hope I haven't spoke well. Never mind. And any questions?